we present XDen-1K, a density field dataset of real-world object. This is the first large-scale dataset of real-world object. Each object has its 3D model, biplanar X-ray map, and corresponding density field data. To start with, we collect 1,000 real object of 148 categories, covering all kinds of daily objects. After object collection, we use biplanar X-ray machine to capture its real X-ray image. We can get two orthogonal X-ray image in less than 10 seconds. We then take multi-view images and use 3D generative model to generate corresponding mesh and then segment it into parts. The mesh is then voxelized into volume, where each part has a trainable linear decay coefficient. We then simulate the X-ray image of the mesh by tracing each detector ray through all parts. The total attenuation of a ray is obtained by summing the per-part path lengths weighted by corresponding linear attenuation coefficients. The tree-based dual-ray source and multiple rays are used together to calculate and obtain the predicted biplanar projection map. Using the captured biplanar X-ray image, we can approximately solve for the LAC of each part. We further convert it into an equivalent density field. Through this pipeline, we can obtain mesh, X-ray image, and density field of a real object. Here are our showcase. The reconstructed density field is aligned with X-ray image. We also propose two subtasks on our dataset: X-ray conditioned volume segmentation and center of mass-aware robot manipulation. Based on XDen-1K, we additionally collect a synthetic data of 7.6K object, annotated its material, and simulate its X-ray image. Using the data, we fine-tune part field. Part field takes mesh as input and generates triplane feature. We additionally take X-ray image as condition and cross-attention original triplane latent on X-ray latent. We then train an MLP head to decode density and apply k-mean clustering to segment the given volume. We find that conditioning on X-ray leads to better segmentation result in both synthetic and real data. From our density field data, we can easily evaluate center of mass and moment of inertia. We further demonstrate how interactions applied at different positions relative to the center of mass affect an object's motion in 3 real robot subtasks. When the grasp point is off the center of mass, a moment is generated that makes the hammer rotate. While it's stable when grasped near center of mass. When the center of mass lies away from the contact point, gravity generates a moment. The cup tips when placed with large tile angle and stays upright when placed with small tile angle. When the push point is higher than the center of mass, it generates additional moment. High pushes lead to tipping, whereas lower pushes produce stable motion. We believe our data will be helpful in exploring future X-vision and robot manipulation tasks. Thanks for watching.